Hi everyone, I'm Ahmed Taei from Modeler. Today we'll talk about the work the kernels team, Hanji and I did, to simplify GPU programming with parametric tile levels in Tensor, tile level tensors in Mojo. Before we dive in to make sure that we're awake, I have a small riddle for you. It goes as the following. A unified team of 32 working together for sure to pull through. In synchronized fashion, no threads left behind, executing your matrix multiply with speed in mind. Who am I? I'll give you all a few seconds to think about the answer. And the answer is a verb executing MMA sync aligned instruction. I hope some of you at least got this right. I hope. So let's start with modern GPU architecture. So GPUs are massively parallel machines. For instance, for Ampere, 800 GPUs had 128 streaming microprocessor, each of which had massive shared memory and register files. And this massive parallelism can give you around 2,048 parallel threads to execute. And this parallelism is coming from a heterogeneous set of processing units, so not all cores are executing the same instructions in your ISA. For instance, you have CODA cores that they execute load store, floating point operations, branches, and you can get up to 40 teraflops from those. And then you have a Tensor core, which, as you can see, can give you around 300 teraflops. And they're specialized in executing only one instruction, which is matrix multiply. And the way this GPUs interact with the external system, they had a high bandwidth of chip memory. And as we move in time to the next generations, we have more parallelism. For instance, in Hopper, in GH100, you had more SMs, you had 144. You had more in-chip memory for registers and shared memory. Of course, your cores gets faster, so around 3x faster than previous generation for Tensor core, for CODA cores, and I think roughly around the same for Tensor cores. So you get around 1 betaflop, which is very fast. You also get more specialized accelerators. You get the Tensor memory accelerator to move data from DRAM to SRAM, and you get a higher bandwidth for your external memory. So this all sounds like great news. However, performance is not portable. So if you have your kernel reaching max peak performance in the previous architecture, you need to do a lot of work for this kernel to get the peak in the new architecture. And the reason is you have a new instruction set and you need to apply new tricks. As a result, backends also, not just only kernels, have to catch up very slow. So GPUs are moving faster and the compiler is trying to catch up with the support in the backends. So how do programs use GPUs? GPUs programmed with a single instruction, multiple thread programming model where all the threads are executing the same instruction in parallel. But what the hardware does, it groups these threads into 32 consecutive threads called verbs, then schedule them, hopefully in the best case, and all verbs are executing, a verb is executing all the threads in parallel. That doesn't happens for many reasons in many cases. Or there are also a subset of the instructions that define at the level of a verb where matmul, the one we talked about in the riddle, or when you do reductions or verb shuffles, etc. And also new generations widen that verb. So you get an instruction that is executed, it has to be defined to be executed by more than one verb, like a verb group MMA in the case of Hopper. So single instruction, multiple threads is great in expressing parallelism. We all use it. We wrote kernels and they're fast. But the hardware doesn't really execute threads individually. it groups threads in verbs, and then that's on the hardware side. You also get the programmer. The person who writes the kernel never cares about what each individual thread is going to do. Always write their program where what a group of threads will do. So if you looked at the dense kernels as an example, these dense kernels, like matrix multiplication, they reduce into a data parallel operations on tiles. For instance, when you decompose your matrix multiply or any dense kernel of that flavor, it ends up being an operation on a tile that is assigned to a thread block in a specific way, and then within the thread block, you went to tile again and take this tile and assign it to a verb, and then now you have a verb. You need to assign and organize the lanes or the threads inside this verb to your data. And when you go there, when you map your data to the compute hierarchy, you want to define operations on tiles. Like you want to allocate, load, copy, move things around. So the mental model for the programmer is always at this level of there is more than one thread and there's tiles of data that will move around. And also going back to the beginning of the talk where we saw the Tensor core that gives you 300 teraflops versus CUDA core that gives you 40 teraflops. The programmers want to use these specialized fixed function cores to accelerate their kernels. And the instructions for these cores are defined in terms of a tile. So the instruction itself is expecting things to be on the tile of data, as we're going to see here. For instance, in Ambr, the MMA sync instruction, which does have many flavors for shapes and data types. The one we look at is the 8 by 8 by 16 by 8 by 8. So you will have a verb, which is 32 threads, and this instruction, in this case, will expect data to be laid out in a specific particular layout. For instance, for the right-hand side, you will have a row major layout for the thread 0 to access 4 elements in that order. And for operand B, you get a column major layout for threads, and it's going to access a 2 by 1 column vector. And then for operand C, you have a layout that's actually similar to operand A. So as you can see, even the instruction itself is expecting data to be represented in tiles and subtiles. So in my opinion, and also what we find as we're doing this, is that sounds like an abstraction gap where the SIMT is kind of low-level details for what you as a kernel developer want to write. So it's just a way to express parallelism. But the way you want to express parallelism doesn't necessarily mean you have to go down and write everything as what this thread should do. Otherwise, you're going to spend most of your time just computing indices and doing index arithmetic and index bookkeeping for how to decompose these things in the hierarchy. So we would love to have a high-level type tensor, which is just fits the problem naturally, where you can do operations in these tensor, like you can tile this tensor, allocate it in a particular memory region, copy it around, do math on the tensor, and when you assign this tensor to the compute hierarchy, you can, once you have a verb, you can say like, okay, so I have a verb, I can use this particular thread layout in this verb. And when you do it this way, now your problem is parameterized, which is great. It's good news for you to kind of like hook your kernel with auto-tuning, because now you have few decisions that you can change, like what is my tile size, what is my register tile size, and so on. So you can like tune your kernel, or even for experimentation, if you're working on something and you're tuning it. And that's not actually a new problem. I mean, software has always existed to write libraries that provide high-level abstractions that they don't have any cost and give you access to express your algorithm or your kernel, in our case, without you have to worry about like the implementation detail of how things will map to single structure multiple data. But because it's a language, because it's a library, the challenge is always in the language. So you're bounded by how much the language can offer for you. And more specifically, in that problem, you're bounded by how much compile time transformation you can do, or how much powerful is the metaprogramming for this library, for that language, when you write your library. And going back to the point where we're talking about the compilers are always catching up, so you don't have always back-end support for the things you're doing, like you're bringing a new, like a new hardware, or even the current hardware actually doesn't, then you're kind of like only left with one solution, which is if you want to access this new instruction, like the new Tensor Core thing, you have to write inline assembly. And you try to avoid that. So thanks to Mojo, it does have a much simpler metaprogramming approach, as we're going to see in a few slides, and also does have raw access to MLIR operations, so you're not only left alone with inline assembly. So our approach to solve that problem, to fill in the abstraction gaps, to define a tensor type that you can tile, distribute to the compute hierarchy, and add more powerful things, more powerful type transformation on it, like you can vectorize it explicitly, and so on. And this tensor type is parameterized by a layout meta type. So you can specify how the data is stored and accessed in that tensor. And for these things to do, you don't really have to have a compiler or a DSL, as long as your language is rich enough to do that metaprogramming. So because metaprogramming is core in that approach, we're going to start with how metaprogramming looks like in Mojo. So let's look at this example where we have almost the same code in Mojo and C++. So in the right side, you have a Mojo code for a tensor type that is parameterized by a data type and rank. And you have a C++ template that is parameterized by a type and a meta type. So in Mojo, we have parameters, which are, they're all meta types. We don't have a type and a meta type distinction between these two. And these parameters are like templates, but they're not the AST substitute kind of metaprogramming approach. They are a compile time value that the Mojo compiler will materialize for you and give you a concrete like typed attribute value. I won't get to the details of how the interpreter works, but there was a great talk by Jeff last year, if you're interested. Another powerful thing in the metaprogramming in Mojo is you have the same language for both programming and metaprogramming. For instance, here in the Mojo program, you have a function that computes the size, or like the number of elements in this tensor, and this function takes a list, which could be a heap allocated object or whatever it is, and all you have to do is to say alias and call size with a list, and that expression will get interpreted and evaluated at compile time, and you'll have a compile time list that is not heap allocated or anything. It's just an attribute list of integers. But in the C++, well, at least in my opinion, it's a totally different language. Metaprogramming, you have to like learn all these different set of language constructs to represent the same thing, and that's a barrier. So for implementing the library, and makes things complicated if you will rely heavily in metaprogramming. In Mojo also, meta types, they don't have to be only user-defined types. You can have parametric closures, which are functions defined in a particular way. And like for instance, you can have a multi-staged MMA where you parameterize it in number of stages and you pass a function to implement things like fusion, which is useful for code generation and for compilers when you do fusion. So we have a tensor that is parameterized by layout meta types, and these meta types are a layout for the data layout, where you specify how the tensor is accessed, and an element layout. So when you promote your tensor elements from being scalars to vectors, you transform the element layout. And the layout is just a function that maps coordinates to coordinates, and that's how you can get the access for your elements. And if you're familiar with cuBLAS, we use a very similar definition for what's a layout. Here's just an example for what's a layout for row measure and column measures. And the reason why there is a tuple, not a list of integers, is because we need to represent tiled layouts as well, which if you're familiar with Erie, the MMT4D back layout, this is similar, but a not flattened version, it's a structured version. So let's look at how do we transform this tensor type. So we have an operation like a tile, where you get a tensor, and you have a tile size parameter and coordinates, and then you get another tensor type, where you evaluate the type by running this parametric function, the tiled layout, and you do this layout transformations. So as vectorization, where you raise the scalar elements to be vectors, and then you also update the vectorized elements, or you distribute a layout. And in this case, the distribute is parameterized by a thread layout, which it's what distribute does, it's tile and distribute. It tiles your data and then distribute threads according to this tile. So now you can define operations in this tensor. Like you can allocate memory, you can do data movement, copy a tile from place to place, you can do math. So let's look at how things come together to simplify how do you use tensor cores to get the max speed performance. So you can have a tensor core instruction, then you allocate tiles in shared memory, you allocate register tile, you have a reduction loop. Then you move data around, you express synchronization explicitly, and then you reduce. And you use the tensor core instruction, you load data to registers, then you compute and accumulate. So how the GPU primitives are implemented? They're MLIR operations, and that's the thing that saved us from just writing inline assembly. So when you put things together, you have a matmul that looks similar to the matmul we saw before. And that implementation did give us a performance that is almost on par with cuBLAS, if not faster in some cases. And just to be precise, these shapes are dynamic, and there is no static shape specialization or anything. And yeah, I think I'm almost out of time for how do we compare against Triton, but yeah, thank you, and I would love to have questions.
Thanks. Thanks a lot. If anybody has any questions, raise your hand. I'll see if I can see you, or come up to one of the two microphones here.
Out of curiosity, have you found some common level abstractions that would be also used for different kinds of heterogeneous hardware? So also think of, say, AMD GPUs, for example, or do you think that also pretty much portable as it is right now?
Yes, so what we described works for AMD GPUs as well, because the only difference is the layout for the Tensor core and the Matrix core. And as far as I know, they're actually similar in some cases. So yes,
Yes, you're easily able to adapt.
Yes,
to the
you can,
layout
you know,
differences.
exactly. So you can swap MMA with the AMD Matrix core. Yeah.
Can you talk a little bit about the MLIR dialects that you lower to from Mojo, like at the top level, and are they upstream?
Right. So we lower to LLVM IR dialect and NVVM for the GPU case. So by the end of the day, things will be Mojo code. The end of the end thing is LLVM IR and NVVM.
Is there a top level dialect too, or are you direct NVVM and
So no top level other than the dialects that used to implement Mojo itself.
Thanks.
So just the language.
Hi, thanks. Very amazing work. I have a question about the layout. For different kind of computations, like the element-wise, we do not have too much reuse. So there will be a linear or just like a water flow through the DRAM to the cache to the register and then go out. While for matrix multiplication, we need to tiling and blocking. From your guys' mind, is there any other communication or reuse pattern that we need to consider for the layout? If we are doing some metaprogramming, we need to maybe doing some derive or on the inference on the layout, how the layout is being computed or translated.
So let me rephrase the question just to make sure I understand.
Say currently we have Tensor Core, and Tensor Core have the different types of matrix computation, and our layout will, based on the matrix Tensor Core, to build up the pattern. And do you guys consider some other patterns for the layout beside the basic underlying Tensor Core?
Right. So we put layout as a way to describe how threads are organized, right? And then if you're doing something like you're copying data from DRAM to SRAM, like you're moving data to shared memory, right? Then we define a composition. Like layout is a function that you can compose with other functions. So you can define a swizzle thing that permute your layout so you can access shared memory in a way that is not going to cause bank conflict. And even if the consumer is just a pointwise op, right? So I agree with you that sometimes like it's not just only Tensor Core that determine what is your layout. It's more of like what operation. And as long as these things are only defined by the operation itself, like you don't need to, like walk multiple operations, then that library approach can make these layouts implicit. So you as a user don't always have to define layouts for everything.
Okay.
So you get Tensor Cores gives you layouts, operations can give you layout, and so on.
Okay. So some of this layout transformation will be mapping to TMA or to some maybe some data layout, or using the thread to do the data manipulation or shuffling in your lowering.
So TMA will do its copy, right?
Yes.
And then we'll just give you data in that tile. Then when you read from this shared memory, you specify the layout for how to read. Did that answer your question, or?
I think answered. Thanks. Thank you.
Cool. Thank you.
All right, we have time for one more short question.
This is pretty short. If you don't mind, could you put up the slide comparing it to Triton? I missed that.
Yeah, which one? Which slide?
The slide comparing it to Triton. The very last.
Oh,
slide.
yeah. Sorry.
There you go.
I was running out of time, so I have to squeeze this part.
All right,
Yeah, sure.
would you like to say anything about that really quick if you've got like a minute?
Yeah, so Triton is a great compiler infrastructure where you can write your program high-level thread block thing, and then the compiler will do an amazing job of giving you a performant code with how much the compiler can do. And our approach is very different. It's a library, so you're still going to write the kernel, and we're giving you control explicitly over all the scheduling decisions you want to do, like you want to allocate register tile, you want to synchronize, and everything, because we are targeting performance first. But I personally believe that you can go from fully explicit, I want to declare everything, and I want to control everything, to something at least partially implicit. Yeah.
All right, that's the time we have. Let's thank our speaker one more time.